All right, so this is the first lesson of the new topic that starts to get into sequences and series, which is probably the most challenging part of this course. So this one doesn't really quite fit with the others, but it's the first kind of topic that veers away a little bit, and called improper integrals. So here is an improper integral. This would be an example of an improper integral. If I asked you to evaluate the integral from 1 minus x from, ready, 0 to 1. This is improper. Why is it improper? Well, remember, the integral symbol means area under the curve of this function from this bound to this bound. So if we look at the actual graph of this and see what we're calculating, we are calculating the area from 0 to 1 under this curve. There's a problem with this curve at 1, and hopefully you can start to see it. If we were to zoom in, it never actually gets to 1. So technically, we are accumulating infinite area because the curve just keeps going up and up and up and never goes to 1. We are just having more and more area. So you may think at first glance that this area just doesn't exist, because isn't it just infinite area if the thing just keeps going up and up and up? There's no area under the curve if there's no top to the curve. But that's not entirely true. Turns out that sometimes we can actually find the area or of an infinite, or we can find a value for an infinite area. Similarly, we're going to be doing that a lot with series and sequences. We're actually going to be finding the sum of infinitely many things can equal a value. So before I show you how to do this problem, two things to know notation wise. If the area exists, then we have to use this term. Let me make sure I get this right. Then we would say that the area converges, and sometimes we'll say converges to a value, whatever the value is. So if the area were 4, the area would converge to 4. But if we do the calculation and it turns out the area doesn't exist, which is going to happen sometimes, as we will see, if the area does not exist, then the other phrase we will start to use for when these things do not exist is we say that the area diverges. And in both cases, we'd say the integral converges or the integral diverges. So we're trying to figure out if this integral converges to a value or if this integral diverges to a value. Now, the terminology is probably more important than the math, because the math's not the hard part. It's the terminology and getting the correct notation as you go through the problem. So especially if you were to do an FRQ on this, the notation's pretty important. Okay, so when you're approaching these problems, this is what you need to do. You look at the bounds and say, okay, what's the problem with the bounds? 0 is not the problem because the function exists at 0. 1, this is the problem. Because you can't plug 1 into this function. If you're trying to find the area under the curve, there's an asymptote at 1. So we need to do a clever little trick to get rid of the problem so that we can proceed like normal. And here's the notation to get rid of the problem. Ready? You let b equal the bound, and you go the limit as b approaches the bound from 0 to b. And now we can do the problem. It's a notation thing because you're not allowed to plug in bounds that are undefined. But if we say, hey, we're not going all the way to the bound, we're going to see what happens as we approach it, then we can determine if it converges or diverges. So you basically just make this little substitution where you plug b in for the spot that's the problem, and then you go through the entire problem like normal. So here we go. Keep the limit the entire time until you take the limit. So we got to find the antiderivative of 1 minus x. That's kind of like a u sub where we raise the power to a half. We're going to need a 2 in front. We're also going to need a negative in front. So negative 2. Check your work quick. Looks good. Evaluated from 0 to b. Keep the limit. All right. And then we just do everything like normal. You keep this. Limit as b approaches 1. Plug b in. And then minus, or in this case it's minus and negative, so plus, and then you plug in the other bound. And now you do this problem. And two things are going to happen. One of two things. Either right here, the limit will not exist, and you're done. It diverges. The area didn't exist. It diverged. It was too much accumulation of area that didn't get small quick enough, which will make more sense later on. Or you do the calculation and there's no problem. So we have to evaluate this limit. It's not a fraction, so we're not going to use our fraction rules. We're just going to try direct substitution and see if it works or not. And actually, this one does. You get -2 times 1 minus 1, which is just 0, plus 2. 1 minus 0 is 1. Square root of 1 is 1. So the answer is just 2. So this area did in fact exist. This integral did exist, and it converged to 2. And we can go back to Desmos and see if that makes sense according to Desmos. So even though, yes, there's infinite area, the area is getting small enough, quick enough, where it almost doesn't factor in. It's microscopically tiny, is one way to think about it. So watch. If we were to try to like play with this and see, okay, if it's 0.9, if it's 0.99, 0.999, 0.999, as we get closer, you can see that value is essentially approaching 2. Basically, it's 2. And then you can try plugging in 1, although I think Desmos rounds it early. It just kind of gives up. Let's see. Yeah, stops there. So the answer is 2, but Desmos has a little trouble with it. That's why we have to know how the calculation works and limits work and things like that to do the problem correctly. Okay, so that's the idea. Just essentially you're finding an antid or a definite integral, but if there's sometimes you have to make sure that both bounds work in the problem. So let's do another example. The next one is 0 to -1 of 1 over x squared dx. Okay, so again, at first glance, you may just want to go through this problem quickly. However, you need to pay attention to whether or not this integral exists for the bounds that have been given. So let's graph this one. X squared, from this time we're going -1 to 0. Yeah, let's just get rid of this. So same thing. There's an asymptote at 0. So how about this case? Well, if you notice, this one's a little bit different. It's hard to see it from here, but it's almost like this one is not closing in as quickly as the last one. And that's part of the interesting thing about these. It looks very similar to the last problem. You're like, well, it's probably going to have a similar answer. Turns out it doesn't. And that's why the calculation is going to be so important. So let's go through it and see why this one's a little bit different. So same logic, identify the problem. The problem is this 0. So we're instead going to say take the limit as b approaches 0 of the integral from -1 to b of 1 over x squared dx. As you go through the problem, do not lose the limit until you take the limit. So the antiderivative of 1 over x squared is -1 over x, evaluated from -1 to b. And then we plug in our bounds, keeping the limit still. -1 over b plus 1 over 1. And then we evaluate this limit right here. In the last problem, we were able to evaluate the limit. We got a number. But what about in this case? If you plugged in 0, quote unquote, plug in 0, top is growing, well, it's 1 over 0. It's not L'Hopital's rule. Sometimes L'Hopital's rule can be used here. It's not cancel. There's nothing. There's an asymptote there. This is dne. So that means that this integral diverges. The area is getting too big too quickly. It's not closing in on a value quick enough, which we'll see more when we start to do sequences and series. So I think if we tried to let Desmos handle this, the integral from -1 to 0 of 1 over x squared dx. Yeah, wow, good. So Desmos, I don't think your calculator would know this. I think your calculator would try to give you an answer, maybe, but Desmos does not, which is good. If you cheated and tried to do -0.001, you're going to get answers. But watch what happens as you make it bigger and bigger. Ready? Watch. So that's ready. You see how as we get closer and closer, the area is just jumping up so dramatically. If that's happening, that's a good indicator that it's not approaching a value quick enough. In the last example, we got closer and closer and closer to 2 with the integral. In this problem, we're just getting gianter and gianter and gianter. We're adding too much positive area. So this integral diverged. Okay, so these are actually the least common examples. The most common improper integral example looks like this. This is the one you'll probably see somewhere on the AP test, where rather than have the bounds being the problem, you're going to have one of the bounds being infinity. And you're going to have to evaluate the area from 1 to infinity of a function, or some bound to some bound. But infinity will be one of your bounds. So again, before we dive into this, I kind of like to think about what is this problem asking me to do. So if I were to graph 1 over x squared from, let's do y. Sorry. Y is less than that. And we're going from 1 to x to, I don't know, let's just start with 10. We're finding the area under this curve, obviously bigger than the x-axis, above the x-axis. So look, we're adding infinite area, but same question. This area is getting so close to the x-axis. Does this area contribute to making the value bigger and bigger, or is it so small beyond this threshold that it doesn't really factor in when we're adding together total area? That's the question. So if we make the bottom bound 1, we can start to see if we're going to get an answer. So if we do, let's say 9.88, 99, 999, 9999. Look at that. It looks like the answer is probably, well, then it gave undefined, but I think the answer is looking like it's going to be 1. This value is not getting bigger and bigger and bigger and bigger. See how it's approaching 1? But here's an interesting problem that's going to be a big one later. If I just gave you 1 over x without the squared, check this out. 9, 9, 9. See how it's just getting bigger and bigger and bigger? It's never staying under a value. That turns out that one diverges, which I'm not going to do right now. We'll probably do that one later. But it looks like this one's going to converge because for all these values, it was staying under 1. So let's see if that's the case. Same logic as the last 2 problems, though. Wherever the issue is, in this case, the bound is the issue because it's infinity. We just do the limit as b approaches infinity of the integral 1 to b 1 over x squared dx. So the antiderivative is not necessarily the hard part. It's evaluating the limit at the end, which really we're going to be doing this a ton, so start getting used to your limit rules again. So antiderivative would be negative 1 over x from 1 to b. Plug in your bounds. So negative 1 over b plus 1 over 1. And now you need to be able to evaluate this limit. Remember, sometimes it exists and sometimes it doesn't. So in this case, this one's nice because it's polynomial. Just remember your rules for polynomials. Where is the biggest power? It's in the denominator. So this one's end behavior is 0. So this limit goes to 0. And 0 plus 1 is 1. So this integral converges to what? The answer is 1. And we would say that the area converged to 1 or the integral converged to 1. Okay, so that's the idea. Basically, you just got to remember that, okay, as we start to do definite integrals, if you see ones like these where there's an asymptote in the problem, pay attention to whether or not you're accumulating over the asymptote or up to the asymptote. And then you have to use a limit in order to mathematically deal with the asymptote. Go through it like normal, and then plug in and evaluate the limit by direct substitution. If that doesn't work, remember your limit rule. Sometimes L'Hopital's rule can apply. A lot of times it's your end behavior rules, though. And the biggest, most common problems are ones like this, where the bound is infinity. We are accumulating infinite area, but the area gets so small at the end that sometimes it can actually converge. And in this case, it did converge to 1. And again, you got to remember your limit rules here. All right, and that's it. We will do more examples of this, but this is the very beginning of the super fun sequences and series part of this class. All right, that's it, guys.